Hi everyone. We've just done some sound checks, but I'm just stalling, anticipating somebody rushing around the corner to tell me that they can't hear me. But if that doesn't happen in the next few seconds, I'll carry on regardless. Thumbs up, here we go. Welcome everybody that's managed to join us. My name is Robert Deffley. I'm Principal Engineer in Advanced Metals Processing. I'm going to talk through the complex umbrella system that is my role in material science and engineering, and then in another role that I have that's national facing, part of the Henry Royce Institute. This is hopefully one of many monthly facility tours that are going to happen across faculty and AMG. So I'd like to thank David and Ed from the Nuclear MRC for enabling this to happen. And if there's anybody watching that's interested in doing this, I'm sure they'll be happy to hear from you and plan future virtual tours around the faculty. So I'll crack on. So like I say, my primary role is Principal Engineer in Advanced Metals Processing, and then I have a Technology Platform Lead role in near-net shape processing. And I'll explain what that means in the context of the facilities that we've got here in Sheffield that are part of a bigger network of facilities and materials research. So we're part of Material Science and Engineering in the Faculty of Engineering. So for anybody outside of materials, we're an interdisciplinary bunch. We're the intersection of chemistry, physics, biology, maths, and engineering. And we're all brought together under three main topics or themes or pillars that we work towards in the department. So that's materials for medicine and health, materials for society, and materials for extreme conditions. So our ambition is to deliver materials for a sustainable future, but we cut across metals, traditional metallurgy and advanced metals, ceramics, biomaterials, nuclear materials, materials for energy, battery materials, cements, natural materials, spiders and snails and slugs and all sorts of things. So like I say, a very interdisciplinary bunch, but we have these common goals that we work towards. And then just on the right hand side of the screen there, to blow our own trumpet, we're ranked first in a lot of things as well. So we're getting the pat on the shoulders every time somebody checks on what we're up to. As I mentioned before, we're part of a national network called the Henry Royce Institute, and that's enabled us to build two brand new facilities. So this is where we host a range of new equipment. We've got two facilities, the Royce Discovery Centre that we're going to have a look around today, and the Royce Translational Centre that's out on the university's Innovation District on Sheffield Business Park out towards the motorway. So the left-hand picture there is the RTC, and we're currently in the RDC on the right-hand side there, which is on Portobello Street across from the Amy Johnson building. So the Henry Royce Institute was set up with a mission to promote world recognised excellence in the UK for materials research and accelerate that to commercial exploitation, and ultimately to deliver positive economic and societal impacts. And the main routes to doing that are through enabling the research, through funding mechanisms, through providing access to the latest facilities, and as I say, the RDC is one of those facilities. Looking at collaboration and building those collaborations with intermingling with the academic community and the industrial materials industries, and then fostering and developing skills in materials. So Royce is like I say, a national network led by Manchester, University of Manchester. So that's where the big hub building is. And as the infographic shows, we're keyed into the UK universities and then to the RTOs and industry elements in the materials world. But the other partners are listed there. So Sheffield's the second biggest beneficiary of the original pot of money, alongside Manchester. Then we've got other facilities that have been built or enhanced at Imperial, Leeds, Cambridge, Oxford and Liverpool, and then National Nuclear Labs and UK Atomic Energy Authority. And then since the conception, two affiliate partners have joined in Cranfield and Strathclyde via the AFRC. So it was £300 million worth of investment in new facilities by EPSRC. And that was 7 years ago that everything kicked off, and we've pandemics aside, we're moving into our operational phase and getting most of those facilities interconnected and joined up, and loads of initiative coming up in the last year and in the couple of years to come. So how we're structured around materials then is we've got the national materials community and then the national materials challenges as our driving force. We're split into key Royce research areas. So advanced metals processing is what I'm part of. Here at Sheffield, we've also got biomaterials and nuclear materials activities and facilities as well. There's multiple other areas that are key that are led by the other partners. And then cutting across all that, there's imaging and characterization. So there's facilities outside of the RDC and the RTC in Sheffield that have been enhanced with equipment from other research areas, but also lots of advanced characterization capabilities as well that hopefully will be subjective tours in the future. Within those research areas and within the facilities that have been established, we've defined technology platforms. Within advanced metals processing, we have three. So there's near net shape processing that I lead, and then we've got materials discovery and prototyping and thermomechanical processing. That was the last one we have some capabilities in, but is led by Manchester. And we have another technology platform lead in the University at Sheffield, which is characterization of radiation damage of materials. So the other, my colleagues who are other technology platform leads are Kathy Christopherdue and Amy Gandy on those other two technology platforms. So advanced metals processing. So we're getting to what we actually do at the RDC. So we've got the capabilities to go from primary production of metals through intermediate processing, component manufacture, and then post-processing and characterization. So I'll just give you a bit of a schematic overview of those before we go and see them in real life via Ed and his camera downstairs. So this is how we're set up. So advanced metals processing, the orange boxes at the top of the three technology platforms under the AMP banner. There's also powder production there as a strand, which is an enabling theme that's not classed as a technology platform in its own right, but kind of cuts across the two either side of it. So within those categories, we subdivide them, and then ultimately at the bottom, we've got different bits of equipment from melting alloys, making powder, functional shapes, and some more traditional processing. And where those change from green to blue, it's where we start to look at capabilities that span across Sheffield, Manchester, and AFRC as well. So one of the key things that we want to stress, and it's not just contained within this building, but across all of our facilities that have been invested in through the Royce Institute, but we've got the ability to show that we're vertically integrated and we can represent the whole of the supply chain in the metals processing industry as well. So one of the key things that I like to demonstrate is just how these interact with each other. So we've got primary production capabilities at the top, down into intermediate production, powder metallurgy routes for processing, post-processing applications, and then after that we can see how these start to form a circular closed loop kind of process where we can take the outputs of some activities and feed them directly into the other. So that could be through a recycling route, taking components that are at the end of service life and showing that they're recyclable, or taking the waste streams. And that's one of the key areas that we'll see today, where we can take swarf and scrap powder materials and turn those back into functional components without having to go through the melting stage. So keep those closer to the end application without having to go right back up the value chain. That's all I was going to do by way of introduction. There's some contact details and how to follow us. We're also on LinkedIn. My email address was at the start of the slides, and you can contact me directly. I'll put that back up before the end, hopefully. And we'll now try and do the magic wizardry that is get Ed involved and have him displaying what we have down in the RDC metals processing shop floor. So are we good to go, David? Yes. Right. So first bit of kit for us, we've got melting capabilities. So this fits under our materials discovery and prototyping. So the equipment on the...
Are you seeing it?
I can see Ed, but I'm also seeing... Shall I stop sharing my screen? That might help.
Yeah, there we go.
That better, there we go.
Yeah.
So we're looking at our arc melter. This is where we can melt a range of materials at a small scale, so up to around 250 grams of material. So this is where we strike an arc and we use the arc to melt the feedstock materials and the elemental blends that we've got in there. So we can do reactive materials right through to refractory alloys as well. So if I get Ed to just spin round to the table behind him. This is a first for me, so the fact that this is working at all is fantastic. So plaudits to Dave again. So these are some examples of the buttons that we produce. These are niobium silicide samples, so some advanced intermetallic materials there. This is the kind of thing that we make, and we're interested in the microstructures and the phases that form just in that processing at the lab scale. What's key for us is being able to scale that up. So if we get Ed to move on to the next piece of equipment, which is our strip caster or melt spinner. Here we go. So this is the melt spinner, if we have a look inside. So we can do a couple of different activities here. We can do larger melts in a crucible. So it limits us on the type of materials that we can melt, but we can go up to about 1.5 kilo melts and pour through the bottom of the crucible and cast into basic shapes and basic molds. One of the interesting things we can do here is the copper wheel that's in the middle there. That rotates and you can vary the speed, and you inject the molten metal onto that wheel and it cools down incredibly quickly, so of the order of thousands of Kelvin per second. And we can look at non-equilibrium phases and rapid solidification processing, so we can look at novel microstructures and phases that form in non-equilibrium conditions. So if I get Ed to go around to the side, we'll have a look at some pieces from that kind of activity. So the large crucible there on the right hand side, I'll put these in the wrong order for you, Ed, sorry, start on the right hand side. That's the 1.5 kilo crucible that we can melt into, and then and there's the hole in the bottom that we can pour through. The nozzle there in the middle, the one to the left, Ed. That's the one. Thank you very much. That's a nozzle that we can use for the injection of the molten material onto the rapid spinning wheel. And then to the left of that, we have some examples of ribbon. Your other left, Ed. Thank you. So we've got some ribbons that are produced. So some typical applications here are magnetic materials, so quite a hot topic with drives and motors and other magnetic applications, but rapidly solidified alloys in this form can then be further processed, chopped up into pieces, bound in resin and turned into magnetic components as well. Right, Ed, round to the big blue machine, if you wouldn't mind. So then we can start to look at scaling up. So within this facility, we're onto our large scale melting, but this is up to 10 kilos of melt. So this is vacuum induction melting. So on the right hand side in there, we've got the induction coil and the crucible. Upwards a bit, Ed. There you go, thank you. So just sticking out the top there is the crucible, and that's where we do the melting of the alloys. That then tilts and pours, and then if you drop back down to where you were before, that's an example of a square section mold that we've used to cast a material there. So that's an example. We don't do much in terms of casting research. We're more looking at the novel materials or the modified materials that would go on to further processing. If you go to the table on your left, Ed, these are just some examples. So on the left-hand side there at the back, we've got some other examples of parts that we've cast, some more crucibles to the right-hand side. And if you just move across to the right, stop there, thank you. So in the middle there, those tubes look with one that says FE written on it. They are late edition cradles that we can lower in and add higher melting point or volatile materials to the later stages of melting as well, so we can modify alloys during the melt. And then to the bottom right there are 2 aluminium rods that we've cast using a different mold. And then to tie things into the other facility, on your right hand side there, so that mold there is specifically to make feedstock for our gas atomizer. So at the RTC, which as I say we'll be showing on another tour, we've got gas atomization capabilities where we can take cast bars in this case, and we can atomize those using high velocity inert gas. So what we have in the middle is a conical section that we put in the bottom of the mold that just helps us facilitate the atomization process. So that then feeds into, like I say, powder production or traditional technology. So we might take that and take those materials and we can look at hot rolling, cold rolling, forging, or just look at them as cast microstructures. And that feeds into other facilities around that we've got. So we've got hot rolling that's over in the Coral Lab in the Robert Deffley building that'll be moving into this facility in the near future. And then we can hand over to other partners in Manchester and AFRC through the Royce, or anybody that's interested in using those materials. So we move on to near net shape processing and powder processing now. So Ed, if we go back to where you started, keeping you on your toes. So where Eunice has sat there on that chair, that's where we've got our cold isostatic press. So this is a 60 KSI isostatic press, which I think is 420 megapascals. So what we can do there is we can fill a flexible mold with powder or granular material, put that into the chamber, and we can apply an isostatic pressure all over and consolidate that into a solid shape. If you go to your left, Ed, on the table again, here's an example of what we can use. So the yellow mold there will make us a basic cylinder. So that's the kind of maximum size that we can operate in. If you've got a free hand, Ed, feel free to give that a squeeze and show people it's flexible. There you go. And then on the table in front of that, we've got an example of where we've used, this is just a novel ice cube shape, but we've used it to make an elephant. So that's been aluminium powder that's been pressed into a near net shape component, in this case an elephant, for no reason other than why not. But you can imagine a scenario where we will hopefully in the future be demonstrating that we can get more complex molds or more useful components for industrial applications and demonstrate a powder to component process. And that means that we can potentially look at a pre-processing stage that reduces the amount of machining needed in downstream applications and retain properties similar to raw. Not necessarily directly from cold isostatic press, but with some other processing as well. That feeds into, again, we've got hot isostatic press at the RTC that we'll see on another time. But if I get you to turn around, Ed, and go to the next stages, we've got another powder consolidation process, or two, in fact, at different scales. This is the field assisted sintering technologies. So this is our large scale fast process. And to your right, if you look over to the other side, Ed, that is our small scale machine that does the same thing. So in this technology, what we do is we have graphite molds. So we're limited in complexity, but we can get a near net shape, and there's an example on the table of doing this. Those graphite molds, we can put powder inside it, and we have a ram on the top and the bottom, and apply a pressure and heating at the same time as applying a current. So what happens is through the heating, the current applied, and the actual loading applied to it, we can go from 30 to 50 megapascals and up to around 1500 degrees C, but we can process materials from titanium through to tungsten and other materials. The only limitation we've got is the graphite mold will react with the alloy that we're dealing with, so there might be some post-process machining required, or we look at barrier methods to protect the alloy from the mold. So on the table in front of you, Ed, unless they moved it, there we go. So that bag there is full of titanium swarth, and on the small machine, we can make samples from 20 to up to 80 millimeters in diameter if we're looking at a plate. And on the large machine, an example there is a 250 millimeter diameter plate that's laying on the bag. So that's titanium 553 swarth that has been pressed into a solid component. To the right of that, we've got a more near net shape approach. So the left-hand side is a conrod from an automotive application. That's, again, titanium swarth that's been pressed into that preform, and on the right hand side is that same shape after it's been forged. And this is part of an Innovate UK funded project program with Professor Martin Jackson and industry partners. What we've demonstrated there is that they've taken a waste stream of titanium from aerospace and made a viable titanium component for automotive, and it has comparable properties to wrought forged component as it would be made previously, but what it does is reduce the number of forging stages that are required. So I think it was something like a 10-stage forging process down to a 2-stage forging process via a waste stream material. To the right of that, we've got a similar example, but with aluminium. So I think that's aluminium powder or swarth that's been pressed. And then if you can hold the puck on the right hand side, the smaller one, Ed, you might see a shape on the shiny side. You might be able to see where we've put dissimilar materials. There is a pattern in there that's just about visible. So you can see a star shape in there. That's where we've done multi-material bonding. So it's almost like a direct powder diffusion bond process where we've got dissimilar materials joined together. And like I say, the integrity of those components are comparable to raw performance in some cases. And in that scenario, it'd be difficult to forge the biomaterial element of that. So that's the fast process. We move on to the other stream that fits into near net shape processing next, which is the additive manufacturing side of things, or metal 3D printing. So within the facility, we've got 3 platforms. And I'll talk you through those platforms, how they're different, how they're complementary. So this is our RCAM electron beam powder bed additive manufacturing process. So RCAM's a Swedish company that were bought by GE. This process used in aerospace and medical applications. So for anybody uninitiated in metal 3D printing, we take a metal powder, spread it into a thin layer, melt a cross section of a part, and then layer by layer do that in succession to build up the 3-dimensional geometry. The RCAM uses primarily titanium powders, and the size range of the powder, which becomes useful when I put it into context, is between 45 and 120 microns. And if you go to the table, we've got some example parts there, Ed. Walking backwards with those flip-flops on, well done. So these are some examples. So the right-hand side just in front of you, that's an example of an auxetic structure that's been wrapped around a curved surface. So that's a lightweight mesh structure with a good stiffness and rigidity, so good lightweighting properties without a loss of performance. That's been scaled up on the square that's next to it, so it might be easy to see the actual structure within that one. So if you pick up the square piece head and have a look down that, you can see that it's reasonably lightweight and an open structure, but the stiffness in compression for that material was quite impressive. We had a fully grown adult American stand on that, and it didn't fail. And those struts are around or less than 1 millimeter in diameter. One of the killer applications for this technology, if you go to your left there, Ed, there's a acetabular cup from medical implant example. So a company called Lima Corp in Italy has been doing this for a number of years, where you put these kind of mesh structures on the back of a medical implant and allow what they could refer to as osseointegration or bone integration into the back of the implant, so that you get a better clinical outcome than relying on screws and cement. And so you get better longevity of the component. And even though the component itself is made of more expensive processing route, you get a cost saving through the reduced theatre times and reduced surgeon times required for the individual component itself. So better clinical outcome and a cost saving in that example. The black and grey part in front of you there, that's where the group at Sheffield a number of years ago were involved with the British racing teams and developed these with a company called Metron near Nottingham, designed these bespoke handlebars or low volume production handlebars for UK bike racing. So this example is for Bradley Wiggins's world record breaking track attempt a few years back. So this is the bit that was left with us. Obviously, the bit that was used in the race is probably in a museum somewhere. On the left hand side there, where you are, Ed, is just a bracket that we've done topological optimization. That's using a software package called Limit State. That's a spin out from civil engineering, where they can design for minimum mass without a loss of integrity. So imagine a machined part, you would probably make that solid, but for the material savings and lightweighting activities, additive provides an opportunity to make gains in that area. So if you move on to the next one, Ed. Just a reminder, pass to me then, while it's moving over to the next stage. There is a Q&A opportunity at the end of this. So if anybody wants to be dropping questions in the Q&A, please feel free to do that, and we'll field those questions at the end. So this is the second additive platform. So this is one of the lower cost entries into the metals 3D printing market. This is a Desktop Metals Studio Plus system. So this operates much like a metals 3D, a plastics 3D printer that you can get relatively cheap these days. So inside there, you've got two nozzles. So the feedstock drops into there and the nozzle heats up and softens a polymer binder that's got metal powder embedded in it. And then you extrude out a shape to create a green part, similar to how metal injection molding would work and other processes. So you've got metal powder in a binder that's been shaped. It then goes through a two-stage debind and sinter process. So the next unit there on your right is the solvent debind. So we leach out one component of the polymer binder, which is, I think, wax-based, before we then take it out of that and go into the furnace where we do a thermal debind, and the furnace is this unit just here. And so once the polymer starts to burn off, the metal powder particles start to come into contact with each other, and then in solid state they fuse together and then densify, and we end up with a fully metallic component by the end of it. So you go to the end of the bench, Ed, there's a couple of examples. So on the left-hand side is a cartridge. That's what contains the feedstock. The stick there at the side is the feedstock. So that drops into the nozzle and is extruded out to create the shape. And then we've got a couple of examples of as printed and sintered parts. So we've got a relatively rough surface finish, but we can make reasonably complex assemblies and complex geometries even on this more crude process in terms of the deposition resolution. But these components can then be polished. So these, the right hand side are the same components that have been through a electrochemical physical slurry process by a company called REM Surfacing, and we get a very high gloss finish on those. And the lizard there it's almost jewelry-like in how it moves in comparison to the as printed and sintered part. But it demonstrates that the underlying materials of good integrity, so the surface finish after the polishing is good. It is standard powder metallurgy applications that we're looking at, so some level of porosity is anticipated, but we can do further post-processing such as hot isostatic press to close that up where it's relevant. And so on to the last bit of equipment in this facility, we've got two laser powder bed fusion additive manufacturing machines. So we've got an Econity Lab and an Econity Mini. So these are the most common additive manufacturing platform probably in the market in use is the laser powder bed fusion process, but these are more experimental bits of hardware. So these are a bit more open source, so we can play around with them with different instrumentation. They're not locked down to specific parameters, and we can develop materials on them with relative ease. So the one in front of us has got a heater build chamber that's capable of going up to 1200 degrees to give us another level of flexibility. It's a relatively small platform, so we're limited in the size that we can do, but we've got multiple versions of this type of printer within the university, particularly at within the AMRC as well, so we can start to hand over and do scale-up activities in conjunction with our colleagues up there. As well as the kind of laser and the scanning capabilities, we've got in-process monitoring built into these, where we are able to use that data, and we're developing on-the-fly processing where we've got machines that are almost autonomous in terms of their parameter development. So we can take information from the melt pool, from the thermal imaging and things like that, and pyknometer, to feed back into a closed loop control process or a series of control steps that will optimize the parameters based on a set of defined criteria that we can input. And this is helping to expedite the development of new materials. If you just turn to your left, Ed, there's an example of the thermal imaging camera that we've put on there. Yeah, so we developed a new lid for the system, and the grey box on the top is thermal imaging camera with a boroscope, so we can see the melt pool, and that's been done in conjunction with electrical and electronic engineering, our colleagues over there, through an ATI project. If you go over to the table the other way, Ed, behind you, we've got some example parts here. Again, we've got another lizard, just because it became a bit of a thing when we start using the printers to print a lizard. So that's a smaller scale version to show that we can get better resolution from the laser powder bed machine. some interesting examples. If you look at the front, the mirror in front of you, Ed. So this is different stages of optics for satellite applications. So the left-hand side component was made on the E-beam platform. And that's in a light-weighted version of the mirrors that we're looking at. But if you, Ed, if you mind just holding that up to the side and looking at the mesh down the middle, if you've got a free hand. So there we've got a honeycomb or a mesh structure to provide light weighting. The next evolution of that project, working with the design prototyping group, did topological optimization to support the back of the round section in the middle, which is going to be polished. And so you can make that section thinner and thinner and thinner to make it lighter, but it's not then strong enough to tolerate the loads to do with the polishing or the machining stages to make it, to give it the mirror finish that it requires. So they could optimize for the weight and the loading on the back of that as well. If you look at the one that's been polished, that's a demonstration that we can actually get incredibly good mirror finish through post-processing on additive parts. Difficult to show on the camera, but yeah, everybody's welcome to come see it in person further down the line. And then another project, the snowflake looking design on the right hand side is actually, you see though the gaps in between the nodes there, we could put piezoelectric actuators in there and actually deform the mirror that would be on the back of it. So this was a collaboration, I think, with a French university, again, so that we could develop a component that was had some level of adaptability in process through the use of different actuators in there. On your left hand side, Ed, there's some round samples. So this is an example where we've been looking at expediting parameter development as well. So as well as using the in-process monitoring, when we have to validate the materials, we've come up with a process to expedite the validation of that as well. So these samples are deliberately designed to contain a design of experiment at different parameter sets. These then drop straight into our metallographic sample preparation equipment. And then within 3 days, we can get that turned around from the machine to the polishing and onto the microscope and automate the image capture and then automatically pick out which parameter sets gave us the best integrity part or the lowest porosity part. To the middle of the table, Ed, there's some the copper colored parts at the front there first. These are, we've managed to 3D print copper, which is difficult. Most people rely on a blue or a green laser, which we don't have at the moment, but that's a PhD project that's been delivering some work for electrical properties and thermal properties and magnetic properties and looking at drives and motors. This copper section, these copper coils have been utilized in an array to do some drives and motor work. And then in the space sector, the larger components at the back, these all stack together. I won't make you do it one-handed, Ed, but these sections all stack together to give us a rocket booster or thruster to go into the Sunfire project that's run by some students at the university, sponsored by a company called Alloy that's supported the work. And they've used additive manufacturing for this component to put complicated internal structures to give us efficient thermal management of the component. And then just to shout out to a platform that we've got across the road in the Quarrel Lab in the Robert Deffley building. The components on the right hand side, Ed, the darker colored ones, this is where we've got our 5-axis blown powder deposition 3D printer. So this is where we, rather than the powder being laid down in layers and melted with a heat source, we blow the powder through a nozzle that the laser runs down like a laser cladding process, and we can use that for component fabrication, but scale that back and do single layers for surface modification, and then in between that we could do repair of components as well. So a lot of work in the aerospace industry for repair of components, but quite complex geometries possible with that process as well. And so hopefully that's a flavour of all the equipment that we've got in the metals processing workshop. The RDC itself does have all the labs on the top floor that, again, I think we're going to do that as a separate tour in the future. Lots of characterization, various ways, nano investigation and X-ray labs as well. But we've got here the ability to develop novel metals at the lab scale and start to scale those up, and then look at turning them via powder metallurgy routes into functional components or near net components that feed into the supply chain. So hopefully that's a taster. And in conjunction with our other facilities, these tie into a broader range of activities that we've got here in materials and part of the Henry Royce Institute. Yeah, I'll put my slides back on so that we can get contact details, and then I'll let David tell me if there are any questions. No questions as yet. So if I thank Ed for his camera work, and if I got to share my screen. Oops. There we go. So they're the main Royce points of contact, or it's robert.deffley@sheffield.ac.uk if anybody wants to get in touch with me. And if we don't have any questions in the Q&A, I'll let the emails roll in, and thank everybody for attending. If not, we're good to go. Right, thanks everybody. Hopefully that came across okay. Any feedback you can send to David and Ed at the Nuclear AMRC. So but thanks for joining us.